All right, well, it's my pleasure to introduce to you Dr. Kimberly Arcand. Dr. Arcand is an expert in astrophysics data visualization and has been a pioneer in 3D printing and extended reality applications in this field. Kim began her career in molecular biology and public health before moving to NASA's Chandra X-ray Observatory with the Center for Astrophysics and the Harvard Smithsonian in 1998. She led the production of the first ever 3D print of an exploded star using NASA's observational data and launched the first ever data-driven virtual reality application of a supernova remnant using NASA data. Arcand is an expert in studying the perception and comprehension of high-energy data visualization across the novice expert spectrum. I'm learning a lot of new words here. He has also co-written 7 popular science books, including 2 children's books, which are in my Amazon cart right now. I'm so excited. And with that, Kimberly, go ahead and pull up your slides. We'll make sure that's working.
Great, and hopefully my sound is good.
Yep, you're sounding good. And then I have your video link whenever you're ready for that. So.
All right. And can you see my screen?
Yes.
Okay.
Yep.
Well, thank you so much, Amy, and thank you everyone for stopping by today. I'm really excited to talk about the type of work I get to do for NASA's Chandra X-ray Observatory at the Center for Astrophysics, Harvard and Smithsonian. It is a bit of a mouthful, but we really do get to do some fun stuff. So I'm going to talk about some pipelines that we've been working on for 3D modeling that lead us to 3D printing and also XR capabilities as well. So just to lay a little bit of a groundwork, my work deals primarily with the high energy universe. So really energetic things such as exploding stars and colliding black holes, clusters of galaxies, that sort of thing. The toolbox essentially that astronomers have to understand the universe is pretty large, and there are many different kinds of tools. When it comes to light, there are many different kinds of light to study from. So Chandra looks at the universe in X-ray light, but other telescopes such as Hubble might look in optical light or near infrared. The Spitzer Space Telescope used to look at infrared light, etc. So all of these different kinds of light just provide us with a tool to be able to capture data. So this is an image of the Chandra X-ray Observatory, which is about the size of a school bus. It was launched back in 1999, and it's been doing just incredible science now for over 20 years. It goes about a third of the way to the moon at its farthest distance from Earth. So again, pretty exciting topics that we get to look at with Chandra, from exploding stars and black holes to things like colliding and merging galaxies. Very energetic things in the universe. But essentially, it's just like a data treasure chest. After 20 years of a mission, particularly, our data archives are now just this very, very rich and mature set of data. It's just like a treasure chest. So for us, the process of getting from a object in the sky that we're studying to some sort of data output takes a series of steps, but it all starts with the binary code, the ones and zeros that we use to be able to talk to spacecraft, essentially. So we are happily drowning in data. It's a pretty positive place to be, and I'm going to take you very quickly through a few of my favorite sites to see in the universe, from stellar nurseries where baby stars are being born and growing up and eventually leaving the nest, to more mature star systems, stars that are ready to explode, stars like our sun that are on their way out and sort of passing on to the next stage of their evolution, stars that have exploded because they were really massive and got old and ran out of fuel, pulsars and magnetars and black holes, galaxies of all shapes and sizes, from pinwheels and exclamation marks to starbursts and antennae to whirlpools. We have things like black holes that are merging slowly over time. We have things called the Death Star galaxy that is essentially a very high-powered jet from one galaxy is kicking out from the supermassive black hole and hurting another smaller galaxy nearby, unfortunately, to very large objects, massive X-ray jets, clusters of galaxies, and even clusters of galaxies that look like they're smiling back at us thanks to gravitational lensing. So we have a lot of fantastic data, but I'm going to focus in now just a little bit on one particular object that is a dear friend of mine, Cassiopeia A. This is a star that exploded. Essentially, stars that are very massive, they live their lives over many, many millions and millions of years, and eventually they start running out of fuel. Their core collapses and then they can explode. And that's what happened in the case of this supernova remnant, Cassiopeia A. So we're looking now at one of the earliest stages of data processing that essentially brings us the image or the visual representation of what that object looks like in 2 dimensions. We, of course, start out looking a little bit more raw than that, but after doing some processing and color mapping, we get something that looks like this. But one of the really great things about astronomical data is that there's many different kinds, and especially if you're doing longitudinal studies or looking at an object over a longer period of time, you can do things like pay attention to how that object is evolving, for example. So we know that the supernova remnant Cassiopeia A is expanding out at a pretty prodigious rate. But what's really fantastic about Cassiopeia A is it's sort of nearby, at only about 11,000 light years away. It's local in our Milky Way galaxy. We have a fantastic view of it, so to speak, from our position here on Earth. And because of all of these various elements, we are essentially able to recreate that information that we have of the object into a 3D model by understanding which of the light is moving away from us and which of the light is moving towards us. So this 3D model was originally created by Tracy Delaney, who was at MIT at the time back in 2009. And we've worked with models like this ever since, because this was a bit of a turning point for us to be able to start thinking of how to present this information in a 3-dimensional model. But once we had this 3D model, we started thinking, you know, what could we do with this? And some friends of mine at the Smithsonian around then, back in the late 2000s, early 2010s, had just 3D scanned and 3D printed President Obama's head. And I thought, well, if they could do that, I'm sure we could figure out how to 3D print this exploded star. So after some trials and errors, we took this 3-dimensional model that we had of Cassiopeia A, and we figured out how to 3D print it. And it was, I think, one of the most incredible things to be able to take this object that I had been looking at for so long, because Cassiopeia A was one of the very first objects that the Chandrasekhar Observatory ever looked at. So I was very familiar with the data, and to be able to hold a version of it in my hand was just a really incredible moment of a new type of understanding and awareness of what that power of 3D printing could be. I think for me too, with this 3D print, of course, you do have to add a bit of a disclaimer that in real life, of course, the supernova remnant is not in a PLA filament, it's not plastic, and it is much, much scaled down. In real life, this object is about 40 million billion times the surface area of our sun and planet. So clearly you would never be able to hold the real thing in your hands. But for an object that is so seemingly esoteric, so abstract, and so nebulous, quite literally, and also so distant, it is a really, I think, useful way to be able to bring that star down to Earth, in a manner of speaking. So this actually launched a whole program, just this one object that we were able to understand in 3D, launched an entire program for us on the communication side. And also since then, we've been sort of collecting more and more objects in 3D from the research side as well, because it has that sort of dual importance. You know, you learn things when you can understand them in 3 dimensions on the research side. For Cas-A, for example, the researchers understood now that this star was coming apart in phases, right? And this remnant, so to speak, was the spherical part, of course, was really important, but also those jets that come out from it on these polar jets were also really important to be able to understand that those were 2 sort of separate processes going on. So we started working in 3D pretty diligently at that point. We started pushing the different kinds of 3D printing that we could do. We started experimenting with powder printing, for example, because we wanted to be able to preserve some of that color information. The color information on a astrophysical image like this really does have value. In the case of Cassiopeia A, we can actually color code by chemical elements. So the iron, the silicon, the sulfur, the argon, those types of chemical emissions during that change and dissipation out into the universe, that information has value, just like a weather map on, an app on your phone or on the nightly news has value when you see the color coding by, say, temperature or wind speed or precipitation level. So the powder printing was one of our first ways to be able to preserve some of that color information. We also experimented with texturizing it. And that's when we started working more with some of our community members who are either blind or low vision, as a way to be able to provide this information with them in a much more accessible format than we had been able to before. So I like to think of Cassiopeia A as sort of our breakthrough object. We eventually took it into extended reality as well. We brought it into virtual reality. This is one of my students here that is walking inside this exploded star, and she is able to learn about this object in a very different way. And that, I think, has been really, really exciting. And other types of extended reality, like augmented reality, in this video right here, we're actually watching someone build the layers of Cassiopeia A in their office, or it could be their living room for all that it matters. But you'll see in a second, as they get a little closer, you can essentially turn the layers on and off for the silicon, the sulfur, the calcium, the argon, so that you can build or, sort of combine those layers one by one. You can isolate them, you can turn them around, and you can navigate through them. And we started working with other types of extended reality, such as holograms, for example, again, as another way to be able to communicate and also learn from this information. And you can just see really here a short snippet of what that screen-based hologram looks like, which gives us the benefit of three-dimensional display, but without needing any headsets or other equipment or have to touch something, as in during the time of pandemic. So another thing that was really useful to us when we started considering these 3D pipelines and how this data processing could work out was during the pandemic, we definitely had to do a bit of a pivot. We had been working with large communities of students and other learners who were either blind or low vision. And during the pandemic, that did have to stop for us because we did not have the mechanism to be able to 3D print in large quantities, to be able to just give anyone their own dead star that they could hold in their hand. So we did pivot to data sonification, which I believe the sound will not play through, so we can pop over to YouTube. If you're not able to hear that data sonification like I can. But essentially, it's a way to take that information and to add one more layer to it by translating it into sound. So somebody who's visually impaired could still access it. And I'll be honest, this pivot to data sonification during the pandemic was huge for us because it went completely viral, which we had not expected at all. We created it for a community that we had need of being able to continue to work with during the pandemic when we could no longer do 3D printing at scales that we had been used to. But it really turned out as an excellent example of when you create something for one group, it really does help make it useful or more accessible to other groups as well. So data, we have all of this data, and again, Cassiopeia A was sort of a turning point object for myself and for my team, but we have since then been able to work with many other objects as well, different kinds of supernova remnant explosions, for example, through different mechanisms. This is Tycho's supernova remnant, also a really fantastic supernova and relatively nearby in the sky. I think it's about 15,000 light years away. Right now, we're just sort of stepping through some of the data processing mechanisms to be able to understand that depth information, or again, which is moving away from us and which is moving towards us. And then we worked with some fantastic colleagues in Japan to be able to include simulation data to constrain that information to be able to create yet another 3D model, and then to go ahead and 3D print that again. So we were essentially expanding our library of 3D printed objects. And Tycho Superremnant is another great example of some of the interesting things you can do with it. For Tycho specifically, we have essentially two pieces. We have the ejecta, and then we have that shock or shell that's around it. So being able to have two pieces of that supernova remnant, visible and tactile, was very useful. And similarly, once we sort of adjust it into a 3D pipeline, we were able to bring it into some of our extended reality formats as well. We've done this with other objects, again, continuing the theme of one of my favorite types of objects, which is exploding stars. This is another one called Supernova 1987A. It's a fantastic print because for this object, when we're looking at it face on from Earth, it really looks like a donut and it looks rather plain. But then as soon as you're able to combine the simulation data that's been constrained by the actual X-ray observations, then you can look at it from all angles and you can see that it really does not resemble a plain donut, but instead looks more like a crown with all of these filamental bits and pieces that are coming off of the top and bottom of that ring. So it is one of those objects that can look awfully plain from our perspective here on Earth, but when you understand what it's actually doing, you just understand a lot more about the processes that are involved. Other objects as well, this is the Crab Nebula and Pulsar. So this is the leftover core, super, super dense, made of neutron stars. It's made of neutrons. The core, called a neutron star, is essentially, if you took a teaspoon of that material, it'd weigh like 100 billion elephants. Like, it's a crazy density to be able to consider for an object. And it's got this beautiful rotating disk that, again, when you see it in 3D and feel it, is a very different experience than just looking at a two-dimensional image. Other types of star systems, for example, binary pair, so two stars that are sort of dancing together. We've done objects like that. And other teams as well in astronomy. It's not just our teams with the Chandrax Observatory, but other scientists that are using data from the Hubble Space Telescope, from the VLT, and other fantastic tools and programs around the world are doing similar work with stars that are mature, for example, or stellar nurseries, like the very famous Pillars of Creation, where stars are being born in these very tall, nebulous sorts of trunks. So again, being able to expand this library of the three-dimensional information of objects that are relatively far away. You know, we can't just jump in a quick little spacecraft and fly there and zoom around it to get a 3D model. We have to be able to figure it out through a combination of observation data and or mathematical modeling to be able to really, truly know what's going on. Other groups have done some fascinating things, such as with the cosmic web, for example, so you can try to hold the whole universe in your hand at some point, which I think is pretty cool, again, in plastic and scaled way, way down. But I think my favorite part of this entire project has been a knowledge exchange program with learners who are either blind or low vision. We've worked with the National Federation of the Blind and other groups to be able to sit down with these 3D prints and these models and really figure out the best way to produce them, to provide them, and to represent them. So, for example, going back to our good old friend Cassiopeia A, this exploded star over 10,000 light years away from us, and that first model I had up on my screen, it was this one sort of bulky, kind of nebulous and yet hard in plastic version of the supernova remnants. And the first time we worked with students who were either blind or low vision, the first question was, well, I can't access the inside. If this isn't a solid object, which it's not, it's nebulous, it's not solid all the way through, it's hollow, you know, it's more of a shell than like a sphere that's perfectly solid. Well, if I can't access the inside information, how do I really explore this object? So working with those students, we devised a way to just cut it in half, just cut the 3D print in half. And we added locations for some very small magnets around the perimeter of each half so that it could be taken apart, explored both internally, externally, and then put back together with those magnets. And we also magnetize the jets. The jets are kind of thin and a little bit, very filamentally sort of feeling around the two ends, and they can break off easily, particularly when you have to feel your way through to do the mental mapping of how to lay this object out internally in your mind. So we replaced the stick-on jets that came through and that one simple print process. Instead, we have added them as magnetized version as well. So through simple techniques like that, we were able to work with students and better understand the size of the objects. Bigger is better for these type of objects when you're working with students of all kinds, and particularly with the BLV community, the blind and low vision community. Being able to have a really, large, highly tactile object is often beneficial. Of course, in the absence of having something very large, having something small is okay too. Also, just the quality of the 3D prints was important. We started off with an Ultimaker 2 and a MakerBot, and we ended up changing eventually to an Ultimaker 4 or 5 because of the dissolvable substrate was really helpful for these objects specifically because they are so nebulous. They have so many clumps and lumps and bumps that we needed something that was really high resolution, but also with the dissolvable substrate that would make it much easier to be able to produce the print when we're just sort of doing it on our own. We've also had some success working with external 3D printing companies to be able to print these really high quality, again, to be able to work with our learners in different ways. So all of that is to say that we sort of started out with this one curiosity point. Could we take this 3D object of an exploded star, and could we 3D print it? And we have, quite a few years later, about a decade later, ended up with an entire repertoire or a suitcase, if you will, of different 3D models of objects in the universe and 3D prints of those objects that we now have in consolidated kits. These kits we use specifically with audio files and braille and tactile materials like printed on paper. And we have programs that we do with various centers, libraries, and schools for the blind. And it is a very highly enjoyable part of the work I get to do, and not really something that I ever expected to do, but something that I honestly feel honored to be participating in as a way of improving the accessibility of a field that is a highly visual field, but doesn't always have to be. And I think that's one of the best lessons that I've learned from this sort of 3D printing journey, is that something that you always assume has to be one way, a field that has been visual since, people have been sketching the heavens for thousands of years. It doesn't have to be only told or discussed or learned about in that one way. There are these other options through 3D printing, and of course through extended reality, through data sonification, sound, through haptic technology, vibrational technology, in order to take this information on a very sort of different journey. So we have written a paper on this, so I welcome you to check out the paper. It's a review article that kind of highlights a number of different 3D printing and some of the extended reality pipelines as well that other groups have worked on. Again, all this data, I've just happily drowned in it. It's a really wonderful type of work to have. And I'll just, I guess, sort of close down with this idea that representation really does matter, and access to this data really matters. I've spoken mostly today about the 3D printing journey and access to students who are either blind or low vision, but it's not just one group. And as I've seen many times, when you make really strategic pushes to be able to expand the accessibility, you just can get so many more people involved. And just a few years back, one of my daughter's friends said that I didn't know mommies could be scientists. So being here today, discussing with you all these types of projects and seeing what other women in the field are doing has been really inspiring for me as well. I love to talk about these topics, so this is the type of stuff that I get to do in my job and what I write about for fun. If you have any questions on this type of work, all of the material that I've talked about today is public domain, as it's government funded. Again, a really sort of important reason to make it accessible, but I would hope that other people would like to make their work accessible as well. So just some references here if you're interested in any of those 3D models, for example, and you would like to 3D print it yourself. We have about a dozen 3D models available now, and many more, of course, throughout the NASA community. So if you're interested in more NASA models, please do get in touch. I'm currently writing a book on this very topic because I'm so obsessed with it. So I would love to hear from anybody who has questions. And I think, Amy, we can go to questions at this point.
Yes.
Hope I didn't talk too long. Once I get going.
No, you're perfect. Sorry, it took me a minute to get up here. No, this talk did not disappoint. I'm so glad we had you on. We have lots of questions. So the first question,
great.
Most popular question is, are these models available for download? Can we 3D?
They are, and I'm like really excited to share them. Let me bring up again my last slide, which had the URL, and I will paste it in chat as well. Hopefully you can see that. But it's mostly going to be found at chandra.edu/3D print. And if you Google like NASA Chandra 3D prints, you'll find it that way as well. But public domain, please go out there, produce. I would love to know what you come up with. I'm sure with the expertise in this crowd, there are many more lessons to be learned.
Perfect. Next question is, are there any discoveries or revelations that you've made about galaxies after being able to hold it in your own hands?
I think for the most part, it starts with the 3D model more than the 3D prints, just because of that sort of pipeline process, right? And I think what I see in the future, or what I hope will happen in the future, is that pipeline will change so that the 3D print or the extended reality version is not just an endpoint, but is sort of better situated with the 3D model right away. 3D models specifically are really important for scientific understanding and for advancing scientific knowledge. There are so many aspects to being able to turn around, move through, and otherwise know or make meaning from an object you can experience in 3D versus just 2D. And I think there's just a lot of room for growth there. So I would really love to know how this area of interest and research continues. I think there has been a lot of interest from scientists who have different abilities specifically to be able to work with the data in these new pipelines. And so that's, I think, where I'm really excited about as well for an area of research and growth.
Awesome. What software are you using to translate that data, like say all the way from Chandra to the STL file?
There's actually quite a lot of software and also quite a lot of hand coding as well. So we have some specific software to X-ray data, for example, that we use right away, things like Chow and other types of astrophysical processing information, specific software to the simulation data as well. And then when we get closer to like the 3D model, it really depends on what we've done so far, but we might have to bring in like a 3D package like Houdini or Blender or something like that. And then from there, we'll do the tweaking to be able to get to the 3D print. And we've used many different types of 3D print processes. And of course, if we're going into extended reality, I typically like to work in Unity with like C# and Unity scripting. So it's a little bit of this and a little bit of that. It's when we first started working in 3D modeling, we actually, at the time, were using a software program that had been adapted from brain imaging software that was used at local Boston area hospitals. So that very first version of Cassiopeia that I showed you probably looked a little weird and brain-like because we were using brain imaging software. That was all that we had at the time to be able to use. Since then, in the 10 years, 3D modeling for astrophysical data has come a long way, but it's still using a little bit of this and a little bit of that.
Awesome. Can you explain again how that 3D data is collected?
Sure. So with the Chandra Observatory, for example, you're collecting, for Cassiopeia as just one example, you're collecting a lot of data over time. So we have like over 2 million seconds worth of information for Chandra. However, that one 3D model, this one that I was showing earlier, is not just Chandra X-ray Observatory data. It's also data from the Spitzer Space Telescope, which is infrared data, and also from some ground-based optical telescopes. So astronomy in general is very multi-wavelength, and it really is about selecting which tool from your tool belt in order to build that object that you need. So with this object, for example, Cassiopeia A, you just had to be able to figure out from that spectral information, from that sort of DNA fingerprint of light, which of that information is redshifted or moving away, and which of it is blue shifted or coming towards you. And it's tricky to do, and I give so much credit to the original scientist who did that sort of prime development work, Tracy Delaney, in order to figure that out for this very first model. And that definitely set up a sort of key for us to be able to do that type of application to other objects as well. So that has been a really exciting thing to figure out, because again, you can't just fly there in a spaceship and zoom around and take pictures. You really have to be clever about doing it from so far, when space to us is like a giant TV screen. It's far away and it's very sort of flat on the sky.
Great. Well, thank you so much. Great presentation, and just so inspired. So thank you.
Thanks so much.
All right. Thank you.